Okay, welcome to part 2 of the video series Vectorization, Loopless Coding in Python for Data Science. In this particular part, we are going to focus on a very famous problem in data science and machine learning, sometimes known as nearest neighbor sorting. And the concepts we are going to learn in this particular part are also the basis for implementing k-nearest neighbor. Which is a very famous classifier in machine learning. So let me discuss the problem setup. Let me set up the problem, and then you might be thinking after setting up the problem that it may be difficult to write a code for solution of this problem that avoid explicit loops. But then we will see some of the fancy kind of indexing offered by NumPy that actually can be helpful for solving the whole problem very easily, and we can write a vectorized code for it. So let me set up the problem. Consider you have a d-dimensional space, let's say RD. You're working in RD, some d-dimensional space. For example, a two-dimensional space is written in R2, a three-dimensional space is written as R3. So for example, this particular point 0.5, 1.9, this particular point belongs to R2 because it has just two coordinates. A point that has several coordinates, let's say d coordinates, let's say 0.7, 1.9, 34, ... If you have d such coordinates, then this one point, this is called a point, and that point belongs to RD. So in the very general setup, given let's say n points, P1, P2, P3, ... Let's say n points, and each point is from RD. So which means if I think about Pi, it basically has real numbers like A1, A2, ... AD. So that's point 1. So each point basically, in terms of programming or data structures, each point basically is an array of d real numbers. Now the problem is to find out the nearest neighbor of P1, and the distance measure we are going to use is Euclidean distance, which means given 2 points, let's say Pi and Pj, let's say that's Pj, let's say B1, B2, ... BD, let's say this is Pj, and this is, let's say, Pi. The Euclidean distance is defined by subtracting the corresponding entries, taking the squares, and then adding all the squares up, and that is called a square distance. Sometimes people also use the square root on top of that, but normally people use square distance rather than a distance. But nonetheless, the distance between Pi and Pj is defined as the following: summation A. So this k varies from 1 to d, summation AK minus BK square. So that's the square distance, or squared Euclidean distance. If you take a square root at the end of the day, after taking the sum, that is called a Euclidean distance. So that's a number, and that's a distance between Pi and Pj. So the nearest point to P1 is the point that has closest distance with P1. So maybe P2 is the nearest with P1, maybe P3 is the nearest, and so on. So we can sort all the points with respect to P1 with respect to the nearestness of P1, and maybe the sorted order appears like so. So P1 is closest to P1, that's the first neighbor that's the closest point to P1. Then maybe P10 is then closest to P1, and after P10, maybe P34 is closest to P1, and we can sort all the points with respect to their distances from P1. And that is the sorted order with respect to P1. What if we want to sort all the points with respect to every point? For example, we want a sorted order with respect to P1, we want a sorted order with respect to P2, we want a sorted order with respect to P3, and so on. And this problem is what we are calling as nearest neighbor sorting, and we want to find out the nearest neighbors of every point, and we actually want to sort all the points with respect to the distances from every other point. This problem looks like a little bit harder because little bit harder in the sense of vectorization, because maybe we come up with so let me explain how to find out the nearest neighbors of, let's say, P1. All I need to actually go through and find out the Euclidean distance of P1 from every other point. That may require a loop, and I may avoid that loop by broadcasting and find out all the nearest neighbors with respect to P1. Maybe that's simpler. But then if I want to find out the nearest neighbor with respect to P2, all of those, that explicit loop is looking harder to avoid. Although the initial loop was also looking harder to avoid, but broadcasting can help us there. NumPy broadcasting can help us there. But the final loop that actually sorts all the points with respect to every other point, that looks like really harder to actually avoid. But we will see shortly in Python. We are going to actually write that code, and we will see that that problem can be vectorized. Not a big deal. So let's go to Jupyter, and let's actually create a file, a new file, Python 3. Let me name that file as nearest neighbor sorting. Let me name that file as the following, and let me hide that. And all we need is to import NumPy as NP. So next, what we do, let's take an example how we are going to do that stuff. Let's define D. Just for this case, let's define D as 2, and let's define the number of points n. Let's say the total number of points is let's say just take an example. Let's say 3 points in 2 dimensions. Let's define now the points, np.random.rand, and we have n by d. So that's our matrix. These are our points. If we see shape of x, that is 3 by 2. So 3 points, each with 2 dimensions. Now just consider one thing. We have 3 points in 2 dimensions. Let's consider this matrix x1 as x, as everything. Np dot, just we are adding new x's here and then this. And now consider x2 as x, np dot new x's, that is basically np dot new x's, just adding another x's, and this comma that. So now if you see x1 and x2, the shapes may look like a little weird to you, and you might be thinking how useful these x1 and x2 are. But later on in the same video, I'm going to show you that these are extremely useful. So the shape of x1 is 3, 1, 2. The shape of x2 is 1, 3, 2. So let me now see the structure sitting at x1 at the index 0. That structure basically is an array with these values, these 2 values. And now let me see the structure that is sitting at x2 in the very index 0. You might be surprised, this structure basically is a 3 by 2 matrix. So what will happen if I just call the following thing? 0 minus x2, this is x1, minus x2, 0. See, this is the first point, and this is the first point, that's the second point, and that's the third point. So x1, 0 just has 0.1, and x2, 0 has a whole matrix. So what is going to happen is the following. So when I subtract these, actually what happens is 0.1 is subtracted from 0.1, 0.1 is subtracted from 0.2, and then 0.1 is subtracted from 0.3. So this 3 by 2 matrix, this matrix actually is broadcasted into these dimensions, and this has happened just very quickly. And that's the basic idea. If we just have these kind of notations, these kind of shapes, if we make that, then we can simply subtract x1 minus x2, and what will happen is point 1 will be subtracted from all the points, point 2 will be subtracted from all the points, point 3 in x1 will be subtracted from all the points, and all these things will be happen in using broadcasting. Now we can actually move to much higher, after seeing this example, now we can move to much higher dimensions and actually build a nearest neighbor sorting without loops. Let's see. Let's say we have 2000 dimensional space, and let's say we have 3000 points maybe. Yeah, that's a huge thing. 2000 dimensional space, which means each point is represented by 200 real numbers, and we have 3000 points for which we are going to build a nearest neighbor sorting solution. So our x, if you see the x dot shape, that is basically 3000 by 200. Now what we are going to do is the following. We are first going to compute the differences, and these are the differences of first point with all the points, and the second point with all the rest of the points, third points with all the rest of the points, and so on. So the way we are going to do is the following. So we are going to generate actually x1 like so, np dot new x's, and we are going to subtract this from x, np dot new x's, and you might, and this is exactly what we did in here, but here we just did it for the very first point. Now it will happen for every point. So first point subtracted from all of the points, second point here will be subtracted from all of the points, and so on. And that will happen without any loop. That's it. So that's the, it may take a couple of seconds because the matrix is large. And what we then did is we actually, what is happening basically is it is being broadcasted for every point, and the matrix itself has large dimensions. So it may take a couple of seconds or maybe more than a couple of seconds to achieve that. So let's wait for its return. It's taking time. Yes. It's taking time because these are so many, I mean, the dimensionality of the space is too large and the total number of points are in thousands. So it's basically building difference vector from one point from all. So one point from all other 2,999 points, then the second point with all the rest 2,999 points, and so on. So this D actually is returned. If we check, for example, the size of D here, the shape of D dot shape, if we just see that, that is 3000 by 3000 by 200. That means these are the differences, and so the difference of the first point with the first point, and that difference is point-wise, so it has 200 differences. Then the first point with the second point, that has 200 differences, and so on. Now what we can do is we can compute the squared differences, just square differences. Let me call it D2, which is D squared, and that is basically so that's the squares of all. Actually this matrix is so large, it is 3000 by 3000 by 200. The tensor is so large that it may take a huge amount of time to do actually that. And it also depends upon the available RAM at the machine, your memory, because it may have to use the virtual memory and stuff like so, and that will be further, and that may cause further problems of IO kind of problems. So make sure that the sizes of the matrices are in limits of RAM when you're using for vectorized code. And I guess this matrix size is so large. Let me actually interrupt the kernel and actually make the number of points and the number of dimensions a bit smaller to actually get everything worked. It is taking some time for interrupting the kernel, so let's wait for it. Yeah, so let's wait for the interrupt to actually come back, and then we will be actually changing these numbers to a little smaller to get our worked example well. So yeah, Yeah, so it is interrupted. Just to keep the sizes a little bit manageable, let's keep the dimensions high, no problem. Let's reduce the number of points just to keep the sizes of the tensors more feasible. Let's say we have 10 points, and what we do is we do this, that, and that's the shape. And now, yeah, so that's our 10 by 10 by 200 tensor, and then we take the squares of all these. Now, if you see the shape of D2, so D2 dot shape, that is also 10 by 10 by 200, but now we have to add across this third dimension. Here we can use the x's as 2 or x's as -1. So what basically we are going to do is the following. So the discs, the square distances, or let me call that as square distances, eventually is D2 np dot sum of D2, and the x's is either the last x's is 2, either you set the x's as 2 or set the x's as -1. That's perfectly fine. Now if you see the shape of SD, that will be 10 by 10. So now you have distances of the first point with the first point, the second point, first point with the second point, and all these distances available. Now we really need to sort these with respect to the minimum distances. So how can we basically do that? So if we want to sort these in terms of rows, we can use the argsort function from NumPy, and that function looks like the following. So the sorted square distances, oh, that is not sum of square differences, that are sorted square differences, square distances is basically np dot argsort, and we have square distances, and the x's is row wise. So we sort these. Now if we just print these, let's print these sorted SD, you might be seeing like this. So the point number 0, the point at index 0, its nearest point is 0. Then the second nearest is 9 of the point of the point 1, which is indexed at 0. Then we have the third, or we can just add 1 to it just to keep point 1 and so on and all that stuff. We can just keep 1 to it, add 1 to it. And now we have 10 points, for example. So point 1 is closest to point 1, then the second closest neighbor, the second neighbor is 10, then the third neighbor is 6, and so on. Then point 2 is closest to 2, because every point is closest to itself. Then point 9 is its best neighbor, then point 6 is its second best neighbor, and so on. You have seen all this flow, and I have not deployed a single loop in that, and I actually have found the nearest neighbors in a sorted way of every point. And we can also squeeze all that into just one command, the cascaded command. Let me squeeze everything into one command. Let me do that. So that might be the one-liner recipe for sorting the nearest neighbors. So we have this. Then what we really want to do is we want to take the squares. And for that, what we really want to do, we want to add these with respect to the last x's, which is x's, let's say -1. And then we really want to do the sorting. So np.arg sort, that's the, and here we want to sort that with respect to x's equals 1. So that's our final result, which is sorted. Let's say, let me write that as S2, and that's the one-liner for it. That's S2. If you just see print S2 plus 1, you get this. How cool is that? So all that process in just one line. Oh my God, that's awesome, and that's a beautiful one-liner. So And by the way, I will encourage the viewer to actually write the code that requires explicit loops to actually solve that problem, and use the time it magic command to actually test the time difference of this vectorized variant and the non-vectorized variant. You will see a huge difference. And that difference will scale. You will see a huge difference in time, and that difference in time will scale as you increase the dimensions as well as the points. So I hope you like this video, in which we have solved a relatively complicated problem, which was looking difficult to make loopless, but we just wrote the solution in just a single line. Beautiful. There is no loop, and that the solution is elegant. That's one example of vectorization. There are several. In the next part of this video series, we are going to actually solve the problem of corner detection in computer vision. That's a beautiful problem, and making the solution loopless is further beautiful. So our goal is not to understand what is corner detection in the next part of this video series. Rather, we will actually set up the problem of corner detection in computer vision from images, and we will see how the solution actually can be achieved without deploying a single explicit loop. So making that corner detection implementation loopless is really beautiful and really awesome. So let's see the vectorized code of corner detection in our next part of this video series.